Welcome back, everyone, to CSE 234, Data Systems for Machine Learning. It's great to have with us Dr. Jonas Mueller today for our final industrial guest lecture. And Jonas has been at AWS and MSR before. Now he's the chief scientist and co-founder of CleanLab, a new startup that's providing data-centric AI tools to improve ML datasets. He's an expert on AutoML systems and machine learning and deep learning. He got his PhD from MIT, and he's done a bunch of papers at the top-tier AI venues. His work has been featured at several media firms, including Wired, MIT TR, and so on. He's contributed to AutoGluon before, and I came into contact with him while collaborating with the AWS folks and AutoGluon folks. And subsequently, of course, he has co-founded this company, and CleanLab is this open source library that has been gaining popularity rapidly. And we wanted to hear about what you're up to, Jonas, in the space of data-centric AI, which is coincidentally the topic the class is currently discussing.
Perfect.
Take it away. And protocol, students, feel free to post questions on the chat or raise your hand. And Jonas, maybe you can stop and take questions in between.
Perfect. Thanks for having me. And yes, somebody just interrupt me whenever, because I can't really see the chat. So just interrupt me whenever you have a question, and I would love to have it be interactive. Awesome. So yeah, today I'm going to talk about some of the things we focus on in the space of data-centric AI, but of course, the space is very broad and there's a lot of ways that you can improve data. And so today's talk will focus specifically on the annotations for data, which are incredibly important in modern applications of machine learning in industry, which are primarily focused on supervised learning and using data that has been annotated to train models to predict what those annotations should have been in future data. And can I go next? Yes. So yeah, the key idea sort of in data-centric AI versus traditional, what I would call model-centric AI, is that in real-world ML, the data is not fixed, unlike in classes or academic research. And really, your users or your company doesn't care what kind of clever tricks you did to get good predictions on a nice data set. What they really care about is you're going to have a messy data set, and you can basically do whatever you want to it to get good predictions. And that includes fixing different kinds of issues in the data, collecting more data, and things like that. And one big key type of issue that's common in such data sets in the real world is that the labels that are given to you are not always correct, especially when these are derived from human annotation. And this holds even in the machine learning world. In these academic benchmarks, 10 of the top most used benchmarks, for deciding the progress of machine learning research, we found they have very common label errors throughout them. And in the real world industry use cases, this situation is just much worse, right? Because not thousands of people have studied the data that is used in most industry use cases. And you can check out our website, labelerrors.com, and just browse through a lot of the incorrect annotations and labels that we found in some of these very famous benchmark ML datasets. And you can also check out our paper down here, which summarizes that work. And so, yeah, basically everybody knows who's been in data science for a long time that it's more worthwhile to invest in, exploring the data and fixing it up than it is to invest in spending all your time tinkering just with different kinds of models, different training tricks, things like that. And, that's this garbage in, garbage out sort of common sense phenomenon that everybody is aware of who's been in the space. But the problem is people in the past have been doing this exploring and data improvement very manually, very ad hoc. It's kind of like how deep learning was once upon a time, where people had this expertise, like sort of a black magic, and the good data scientists are the ones who can do it really well because they have this intuition and they're really able to fix the data very quickly, guided by their intuition. And then the more junior data scientists or software engineers who aren't formally trained struggle a lot more. And so our goal really is to make this whole process more accessible and more systematic by using algorithms, automation, and engineering principles. And that's really the key idea of what we think of data-centric AI, is to use automation and algorithms to help you systematically improve the data rather than doing it manually, based just on your intuition. And of course, for large data, it becomes very cumbersome to do anything manually anyway. And so some of the hype around data-centric AI, one of the common examples that's pretty famous now was this DALL-E demo. I guess now everyone's talking about ChatGPT, but let's pretend we're a couple months ago and think about DALL-E. This was this famous image generation model from OpenAI that could generate images from text. And as you can see, one of the big complaints in their demo is that they know the data that they're training this generator with is often incorrectly labeled, like a plane being labeled a car, and therefore this generative model was just highly imperfect, because even though you want it to generate a car, sometimes it generates a plane because it was trained on data that had been incorrectly labeled. And again, they emphasize in the demo that, sometimes it generates great things if it was trained on decent quality images and a big data set, as well as accurate labels. And so, yeah, this is sort of common sense. The quality of the labels really matters when you're deploying models in the real world, and more generally, the quality of the training data. Another high-profile example is what the Tesla called the data engine. I'm here taken from some slides from Andrej Karpathy, and the idea of the data engine was Tesla is trying to do this ambitious goal of doing autonomous driving just with cameras instead of a wide array of sensors. And they really focus on just ensuring that they are able to diagnose problems in their data set as efficiently as possible, and then figure out how to fix them as efficiently as possible. And the way they do this is through the assistance of a trained machine learning model. So they have their current data, they train a machine learning model, they use that model to determine problems in the data. For example, noticing that they didn't have enough data in the training set of cars in tunnels, and then they actually use that model to search for similar examples in the data set and add more of those to their training set, and emphasize those examples in the training set before retraining a new version of the model. And so this kind of loop gets you a better and better model, a better and better data, and it's sort of one of the key aspects of their success. And again, just to highlight this difference between model-centric and data-centric AI, in a typical PhD, a student will be very focused on models and algorithms, trying to do well on data sets that are just given to you, either, because the community has decided this is a good benchmark, or you're taking classes and it's just the assignment. But really, in the real world, in a company like Tesla, you mainly end up spending most of your time focused on the data. And so having systematic engineering principles for dealing with data improvement and identifying issues in data is very important, rather than just expecting everything to be done through ad hoc intuition. And yeah, so I'm going to focus mainly on label errors and noisy labels in this lecture. And so what I'm talking about when I say like a label error is, in your standard multi-class classification data set, say MNIST digit classification or ImageNet image classification, you're given some kind of image and it has a label attached to it, which is often given by a human annotator. And so we ran some of the algorithms I'm going to talk about on two of these really famous machine learning data sets like MNIST and ImageNet. And what we found was a bunch of label errors, some of them shown here, such as this 3 was actually labeled a 5 in the data set. This 7 was labeled a 4 in the MNIST data set. There in ImageNet, we had an image of this monkey here labeled as a lion here labeled as a monkey, an image of a bee labeled as an ant, and so on and so forth. And so, yeah, these are very obvious problems, and it's, pretty surprising that there's dozens and dozens of such problems in these very famous data sets that, thousands and thousands of machine learning researchers have been studying for a long time. And we in 2021, just running some algorithms on these data sets found that they have all these label errors in them. And a lot of people in the community were even surprised by this. And so this is, again, just, highly curated machine learning gold standard data almost that everybody thinks is as good as it gets. In industry applications in the real world, the data you get is much worse quality in most applications. The labels have far more errors in them in most applications. So you can go to this website, labelerrors.com, and browse, all the label errors we found in these big benchmark data sets in machine learning. And again, we found these using algorithms that I'm going to talk about shortly. And I just want to go over, a few types of label errors that we categorized when we were looking through these. So one kind of label error here, what we did was we ran our algorithms on all these images from the original data sets, such as MNIST, CFAR, Caltech 256, ImageNet, QuickDraw. And then our algorithms flagged which images they thought were mislabeled. And then we showed those images to Mechanical Turk workers who provided, we provided them an alternative suggested label based on the prediction of a machine learning model. And we asked them, do you prefer the alternative label or do you prefer the original given label in the data set? Or do you prefer neither? And then we categorize the different categories. So the bottom category here are examples where the Mechanical Turk workers did not agree, that either the given label is better or the alternative label we are suggesting is better. And so these you can see are just kind of hard examples. Like you have this yo-yo that kind of looks like a Frisbee. It's very hard to, know what exactly that is unless you spend a lot of time studying it. We also have these examples here in the second to last row, where the Mechanical Turk workers really decided neither of the given or alternative label would be appropriate for this example. And here, for example, in CFAR 100, you see this image of two monks. The given label was rose for that, which is obviously incorrect, but also the machine learning model we had trained gave a totally incorrect prediction of apple. And so really the Mechanical Turk worker, when looking at this, just says, yeah, neither of these apply. And that's actually a constraint of this whole idea of multi-class classification, right? In multi-class classification, you have K categories. Every image has to fall into one of those K categories. And most of these benchmark, there's not like an other category, that's a catch-all. But what happens with these images is they don't really fit any of the K categories at all. And that just is inevitable, with data in the wild. Another interesting example here is like Caltech 256 is a bunch of natural images. And for some reason, we discovered there's like some mathematical plots in that data set, and which are just totally out of place. And so these might be considered things that are, out of distribution in this data that don't belong to any of the classes for which the data set was collected originally. Also, some of these data sets, another limitation, I guess I should say, of multi-class classification is it's assuming each data point falls into exactly one of the K categories. But a lot of these we found actually, two of the categories would apply pretty reasonably to the data set. And so you should always, think critically whenever you're doing a multi-class classification, if it really should have been framed, as a multi-label classification instead, or what's called tagging, for example, tagging different concepts in images rather than categorizing the image to only one of K of these concepts. And finally, there is just the standard label error where if your data really is appropriate for multi-class classification, each image really does belong to one of these K categories. Even then, it's totally possible that the people assigning the labels just got it flat wrong and made an error. Like this lobster here is clearly not a lobster, or this annotated lobster, it was just incorrectly annotated. Likewise, I've never seen an orange dolphin like the one in Caltech 256 up here. And so, yeah, that's what I'm mainly going to focus on for the first part of this lecture is data sets where we are assuming, multi-class classification is an appropriate formulation, and just that some labels have been incorrectly chosen because somebody just happened to choose the incorrect label when annotating the data. And so I'm going to present now the confident learning algorithm that we ran on all these famous benchmark data sets, which is what allowed us to discover, all the stuff I just showed before and all the label errors within these data sets. And so essentially, confident learning is a framework of theory and algorithms for finding label errors in classification data, ranking the data by the likelihood of the label being incorrect, and doing machine learning more broadly when you have a training data set that is noisily labeled, and understanding the structure of the label noise. And if you want to learn more, you can check out the paper linked up top. And so the key idea of confident learning, and more broadly how we think of data-centric AI, is that you can train any classification model, get predictions from that model, and use those predictions as some form of data representation to find errors in the data or issues in the data, in this case, label errors. And so that makes this really, really flexible, right, for all kinds of applications, because we are not requiring anything of how this model was trained. We're not really requiring anything about the data itself. So while I'm presenting everything for image data here, all these concepts translate directly to text data, audio data, any kind of data where you can train a classifier. And also, the performance of a lot of the stuff I will talk about is a bit tied to, how good your classifier is. And that's really actually a big advantage, because people just keep making sort of relentless improvements in machine learning and classification technology. It just keeps getting better and better. And so running the types of procedures that I'm going to introduce throughout this entire lecture, they just get better and better for free as better classifiers come out, versus in a lot of, the research literature, you'll see people proposing new tricks for how to train a classifier in a particular way, or how to modify it somehow so that you can better identify things like label errors. But those tricks are very restricted to certain classifiers, certain types of data, and they may no longer be applicable in the future if somebody comes up with a radically new type of classifier or wants to apply it to a different kind of data. And so I'll jump into a little notation briefly. So here we have the y tilde being the observed noisy label for each data point, y star being the true label that should have been given, which we never observe. And then we have this set X, ij, which is the set of examples in the data set that were given the label I, but actually should belong to class J. And Cij being this counts. And then there's this concept of an underlying joint distribution over these noisy observed labels and the true latent labels that we, never see. And basically, this joint distribution really summarizes the noise process of, which classes tend to have the most noise in them and tend to be the least well annotated. And you can compute the conditionals of this distribution, which, summarize, for example, the probability that label J gets accidentally flipped to label I when somebody's annotating the data. And so obviously the most natural question to think about when we introduce probabilities like this is there's some kind of generative process being assumed, and what kind of processes are we thinking about here when we're talking about incorrect labels? And so one obvious one is just when somebody's clicking in some interface that's providing the label, they just click the wrong thing, just by chance. So we see this like in a lot of the reviews data sets that we've looked at, where you have text reviews, say, of products, and then some star rating for the product. A lot of those data sets, the star rating just totally doesn't match the text at all. Maybe some of you who have submitted papers for conferences have also seen the score from the reviewer maybe doesn't match their text very well either. And also just this is more generally just a class of mistakes, being made in the final determination of this category, 1 out of k categories that each data point should belong to. Another issue is mismeasurement when the data are coming from some sort of sensor. Also, you have in classic data pipelines where you're having humans annotate your data, sort of people who are not trained well enough, or they don't want to spend enough time annotating the data. Sometimes you're getting labels from another machine learning model, actually, or in some programmatic system, and that system is, making suboptimal decisions and thus giving you incorrect labels. And then obviously there's just general noise that can arise through all sorts of processes. So basically what I'm focused on for now is, again, a classification data set where each image is labeled as 1 of k classes, for example, dog, cat, and fox. And some of the images of a dog might accidentally be labeled as a fox. Another example for text would be people labeling, certain kinds of tweets or other text posted in social media. There's these moderators who are classifying the language being used, and they often make mistakes, just because they're moderating, they're expected to moderate a huge amount of text very quickly without being able to deeply analyze any of it. And so here I'm going to briefly talk about this confident joint concept a little more. And so what this is really, it's the count of things, the C, Y tilde, Y star. Remember, Y tilde is the observed noisy label. Y star is the true latent given, true label that you never see. And basically this matrix will be an estimated thing that counts how many times in each data set do we have image where the true label was one class and the observed label was another class. And as you can see, the off diagonals of this matrix would summarize sort of the noise in your data set's labels. And so throughout, we have to make, some kind of assumption here to uncover label noise, because you could imagine in the most general case, somebody can introduce the label noise extremely adversarially, for example, just redefining all the labels, and there's just no way to capture that with machine learning, a data-driven system that doesn't know about the world. And so one of the most common assumptions previously made in the literature was just this idea of perfectly symmetric label noise, where every class is just kind of flipped to another class with some probability, sort of the analog of salt and pepper noise. And what we're going to focus on in this lecture is actually a more general formulation of noise in which the flipping rates of different classes can be different. So, some classes may be flipped, maybe noisy at one rate, while other classes, which are harder to annotate, may be more noisy. A third formulation that I'm not going to talk too much about is instance-dependent label noise, where actually the probability of the label being correct or not also depends on the features themselves. And as I mentioned, in general, handling that is just completely impossible, because you could have just redefined all the classes, redefined the underlying true labeling function, and it would just not be identifiable from a machine learning algorithm's perspective. And so in that world, some people have proposed, additional assumptions that you can add on top of that to be able to make it tractable. But yeah, there's sort of no real consensus right now on what's the best way to make that setting tractable. And so I'm not going to talk too much about it. And so I'm going to dive a little deeper into this process that we just assumed of our label noise being not perfectly uniform at random, but being conditioned only on the given or the true class label of a particular data point. And so here we consider machine learning predicted probabilities from any trained classifier. So we train the classifier, we feed it an image X, and it gives us back the predicted class probabilities of each class. And remember, this model is being trained on the noisy observed given labels, because obviously that's all we have. And so its probabilities must be understood in terms of the noisy observed given labels. And these probabilities will be a function of, or sort of influenced by, the fact that the model is, doing machine learning and it's doing estimation, statistical estimation. So it's going to be imperfect and give you, it has some epistemic uncertainty in it. And also that the label of each example may actually be incorrect, right? So there's also some true noise in the process that the model is capturing when it's being trained on noisily labeled data. And again, without any assumption, there's just no way to disambiguate, is this an statistical estimation error that the model's making, or is it a fundamental noise in the given label for the data point? And that's why we remove this dependency of the noise process on the feature values in the data itself. I think I've covered this pretty well now, but yeah, you get the key idea is that we are making an assumption on the noise process that it is class conditional only and not feature conditional as well. And so let's look at some real world data and just to understand, what kind of what's going on here. So here, what we looked at in ImageNet was a bunch of the examples in ImageNet that were highly ranked by our confident learning algorithm that I'll get into in a second, for being very likely to have label errors. And what you see here for the class pig, if we look at the just some random label errors from that class, is that these are not just being flipped to any other class. Lots of them are being flipped, or lots of them are actually boars, right? But you're not getting some class like keyboard or missile being flipped to the class pig. So that sort of shows you, you know, the symmetric noise is really unrealistic, where you just flip every class to another class uniformly at random. And you can see here that really like the label noise depends not too much on what the actual image data itself looks like, right? Like these look like bores to us. And if you look at other bores, they look very similar. These don't really look like particularly pig-like bores. So yeah, you can see that the label was just flipped to pig, even though these don't look more like pigs than the other bore images in the ImageNet if you go look at them. And so this kind of assumption seems pretty reasonable for a data set like ImageNet. And so just to contrast it again against uniform label noise, what would that look like? That would mean that, you know, you have these data images from ImageNet that are labeled pig, and their actually true labels are totally other classes like ruler or train. And you just don't see that really in most image data sets. So what another natural question is, does this label noise even matter at all? You know, people say deep learning is robust to noise to some degree, like stochastic gradient descent. There's all these theoretical papers.
Jonas, I have a quick question. Sorry to interrupt.
No
So
worries.
the class conditional dependency, do you think that condition on the class, it becomes independent of the features? Because it seems like sometimes people get confused if the image is from a different angle or the resolution is not good or something like that. Basically, even after conditioning on the class, is it possible that the features also affect things?
Yes, so very much so. I want to make it clear this is an assumption. And exactly, if I go back a little, here is exactly where it's written out, that we are just dropping the dependence on the features for the given label. And it is a very strong assumption being made there. And I want to also emphasize, if we don't do that drop and we make no other assumption, then the problem is just entirely intractable, right? Of detecting label errors, because in
that makes sense. So in the image data, in ImageNet in particular, how often do you see this relaxation, this assumption being a problem?
Yeah, so we don't really see that being a huge problem for a data set like ImageNet. As I mentioned, when we run these algorithms on a data set like ImageNet, right, we're not controlling anything about the process which generated it. We're just running it on the ImageNet data set. We find the things that they reveal are, you know, actually often label errors. And of course, also the algorithms may work beyond the theoretical assumptions needed to prove things about the algorithms. That's kind of always true for all machine learning. But I'm also trying to emphasize here with this slide that if you look at each of these images where the given label is pig, these don't actually, like a lot of them don't really look like pigs compared to other images of boars in ImageNet. These are pretty, you know, typical representations of just the boar class in ImageNet, and that's sort of the thing I'm trying to convey here.
Okay, sounds good.
Hi, just as an add-on to what the professor just asked now, for like you just mentioned that deep learning models usually might be robust to noise, like label noise, or that's the assumption, right? So in these kind of situations, don't you think that features that you get from these models could actually like help in the label noise? You just said that class conditional noise, the way you solve it is you don't think of the feature that you use. But I believe that like when a model is trained, it could often happen that like a really strong model could help in sort of like figuring out this class conditional noise, right? So yeah, especially for deep learning model.
Yep. So I'm literally about to get into that. So we are, just to be clear, that is just an assumption on the generative process. The fact that the label noise is class conditional and does not depend on the features. We will actually use the features of the image to determine if it has a label error or not in our algorithm. But to prove things about the algorithm's success, we can only sort of prove things about its success, like its guaranteed ability to detect all the mislabeled data can only be proven under that class conditional assumption, because in the other world where the given label can depend arbitrarily on the features, there's just too many ways to introduce noise that are adversarial and would be valid data sets in other worlds, you know, where actually, if you just flip two classes, for example.
Right. But wouldn't that be solved by adding another like condition to the probability? Like like you have, instead of doing P of like y given y and x that you have in your equation, you add another condition which would restrict it to just that class, just that data set or something, right? Wouldn't that solve the whatever you just said now about like features being represented by multiple data sets and stuff?
So it's really hard, right? You can imagine you have a particular value of the feature that is unique to one data point, say, and then you flip its label only at that value of the feature. So you just never really, detect that, because you don't know if that's the true underlying relationship between the label and the feature or not, because, right, you're always just seeing that unique value of the feature with some value of the label. And it just becomes, yeah, there's not enough data to contradict the label there.
Okay, got it. Thank you.
Yeah, basically, if you're trying to prove anything about these methods, then you need to consider, the worst case scenario. And in the case where the label noise can depend on the features themselves, the worst case scenario is essentially just another machine learning problem that somebody constructed that contradicts your machine learning problem. And you just have no way of knowing that just purely from data, right? That's sort of the idea.
Yeah. Yeah. Okay, thanks.
But again, we're not saying that these methods that I'm going to present do not work in the real world. For sure, there is a dependence on the feature values, right? People are looking at the feature values to determine the label. And so in the real world, certainly the feature values do influence the label noise. And that assumption is just being made for the sake of theory and showing guarantees about when the methods I'm talking about can guarantee to work. Any other questions?
Okay, we have a question on the chat, but Gong Yi has a question.
You want to read it, somebody?
Although the CL loss function is universal, the training of the network is still dataset dependent, so we still need humans to classify the mislabels first. I'm not sure if that question makes sense to you, Jonas. You still need the humans to classify the mislabels first. So your algorithm is outputting the examples that would be candidates that are mislabeled, right?
Correct. Yes.
And then the human has to
the estimation algorithm. Yes.
Okay.
It's all about estimating how noisy the data is, like how many examples are mislabeled, providing you a ranking of the most likely mislabeled examples.
Got it.
And it's up to you what you want to do with that information. But one thing you can do that's fully automated is just delete all that data from the data set and try retraining your model, for example. And we see big improvements when we do that.
Got it. Okay, let's continue, and then we can get back to finish.
Yeah, so really the point of this slide is just to put some context on, a lot of folks were saying that neural networks can just avoid noisy labels and a lot of the research literature. But what they had been evaluating all this stuff on was this uniform random label noise where you just randomly flip the labels. And in that case, it's very easy for these models to ignore the random label noise, and they train fairly robustly. But that really, as I showed it for ImageNet, is not realistic at all in the real world. You basically never have this just random classes being flipped to any other class. And so a lot of the methods that are intended to work for machine learning with noisy labels, they operate. So here the goal is to get better machine learning performance, doing, say, classification where your training data has noisy labels. Most of these methods in the research literature, they operate by changing the model itself or the training process. And so they, have a special loss function. They modify the loss function directly. They do some kind of weighting of the training data. But actually what I'm going to talk about is these data-centric methods that just directly change the data set. So we just train an initial model and then use that model with our algorithm to find what we think is mislabeled automatically, and then just delete, say, all the mislabeled data, or you can correct all the labels of the mislabeled data and then retrain the same model. And we often see you get much better performance that way. And so going back to the confident learning algorithm, remember I talked about counting up how many examples in the data set we believe have true label, say, dog, and given label fox, and converting those into probabilities just by normalization. that's sort of the key quantity we want to estimate using our algorithm. Once we estimate that quantity, we essentially can just say, if we think 14% of the Fox images are, or of the images with given label Fox should have truly been dogs, we can just go then through the list of those images with given label Fox, look at which ones have highest probability of being dog, lowest probability of being Fox from our pre-trained, machine learning classifier. And those are the ones that we would flag as being label errors. And so all we really need are the original given labels in the data set and the predicted probabilities from an already trained machine learning model. And one key thing here is that we want these predicted probabilities to be held out, like out of sample predicted probabilities. So we'll typically train the model using cross-validation so that you're able to get a held out probability estimate for each data point from a copy of the model that was never trained on that data point, just to avoid overfitting. And so the key idea in confident learning is we need to find some thresholds which act as a proxy for the machine learning classifier's confidence on average for every class. And so what this is showing is essentially what we do is we take the predicted probability for all examples whose given label is class J. We ask what the pre-trained classifier, what do you think is the probability that class J would be the given label for this image, when we know actually the image did have label class J. And then we just take an average over all the images in class J, and that becomes our threshold for class J. And so just to give an example here, how the confident learning will work is we're going to estimate a set of, let's go back. We're going to estimate a set of label error for each pair of the noisy label and true label to accumulate those counts that I just talked about in that matrix. And the way we accumulate those counts is we look at for every image whose given label is class I, we look at is the predicted probability for the given label being class J for this image above the threshold for class J, and if so, we then add it to that entry of the counts matrix where we think the given label was class I, but actually the true label should have been class J. So that's really it. So just to walk you through, we start with this count matrix being all zeros. Say we have the following thresholds on the left, TJ here for our three classes. The data set here just has dog, fox, and cow, say, as our three classes for the classification task. And so here the given label would be dog. And we look at the threshold here. And we see that the probability for 0.3 for that class dog is not bigger than 0.7. Then we look at the given probability for the class fox, and we see that the predicted probability of class fox is bigger than the threshold for the class fox, which was 0.7. They're equal here, but we just do greater or equal then. And so essentially that means we think this image is actually mislabeled. And so we think that the confident learning algorithm basically estimates that this image, which had given label dog, should have actually been labeled as a fox. And so we can basically also repeat this for cow. And we see that it does not exceed the threshold and so on. And so I'm just going to skip all the columns that don't meet the threshold now, just to give you a sense of how this algorithm works. And you see that, of course, the diagonals tend to accumulate the most counts because most data is not mislabeled. And yeah, for the fine-grained details, just refer to the paper for confident learning. And I don't want to get too into the weeds here, but broadly speaking, the idea is all the off diagonals of this matrix are what we estimate the label errors to be in the data set. And so let's say we counted all these counts in the data set, we normalize them, and that becomes our estimated distribution of the true and latent true labels and the given observed labels. And from that, we can estimate, the noise rates for every single class, as well as the noise rates for every single annotation overall. Like when the annotated label is dog, by summing up the first row here, we can estimate, and ignoring the diagonal, we can estimate basically how trustworthy is an image where we see the given label being annotated as dog. All this stuff is open sourced in a Python library called CleanLab, and you can run it really easily on a given data set just by providing predicted probabilities from any model and your given labels for your data set. And so here is just a brief comparison on a data set with 40% label noise introduced in CFAR 10. And here the label noise is introduced either symmetrically or in a pattern that's sparse, where basically certain classes have 0% chance of being flipped to other classes. That's sort of this class conditional asymmetric label noise that I was just talking about before. And here we're comparing different variants of confident learning in the top versus all these other published methods that I mentioned are more model-centric and actually try and change either the training objective, the training algorithm, the loss function, something about the model to handle the presence of label noise. And then we're just evaluating the test accuracy on a data set without a test set without label errors. And what you can see here is when we have zero fraction of, so when 0 of the off diagonals of this given true matrix, this given true joint distribution are set to 0, that means we're basically just doing symmetric label noise, where we're just randomly flipping classes to other classes. And when it's 0.6, that means we're doing asymmetric label noise. That means 60% of the classes have no chance of being flipped into another class. And so this noise process is highly asymmetric there. And you can see that the confident learning method, when we train machine learning models by using confident learning to identify the label errors, removing those label errors, and then retraining the machine learning model, and then measuring its test accuracy, we see it doesn't really matter what kind of noise pattern was introduced, and the accuracies remain roughly the same. But for these model-centric methods, they're very sensitive to the kind of noise that's being introduced. And when it's uniformly at random versus when it's class conditional, you get differing accuracies. And so, yeah, we're really advocating for this data-centric approach here of just, it's very dead simple, right? It's just using this algorithm to estimate the label errors, just literally remove the label errors, retrain your model, and then reevaluate its test accuracy, versus these model-centric approaches are far more complicated. They don't just work out of the box for any kind of model and for any kind of data. You really have to tailor them a bit to the model, and it's a lot of work to implement them in comparison too.
I have a small question.
Yeah.
So one of the things that you mentioned earlier in the talk was like, so kind of this, I'm definitely on board with most data sets are noisily labeled, especially in real world settings. I guess my question is, in industrial applications where oftentimes the labels are programmatically generated, not necessarily via a user button click or something, and there's issues there. Is there like a certain threshold on how much noise is tolerable for confident learning to work?
Yeah, so we always assume the data is like diagonally, or that counts matrix I mentioned is diagonally dominated. So all the noise rates do need to be under 50% of the class being flipped to another class. That's a hard assumption.
Gotcha.
Otherwise, the problem is, again, ill-posed if we're training machine learning models from scratch. You can use, pre-trained models that have been trained on massive corpuses of data to try and disentangle certain things. But here we're focused on, any kind of data set where, we don't actually know anything about the classes, definitions, or anything like that. And so it's a really hard constraint, that not over 50% of them are corrupted.
Okay, thank you.
Jonas, I have a quick question too. So this, if I understand it right, are you doing leave one out cross-validation? Are you?
We just do k-fold cross-validation, yeah.
K-fold cross-validation, I see. So when an example is in a test fold, that's the prediction probabilities that you use for that example.
Exactly. So the key challenge is we don't want to use predicted probabilities from a model that was trained on this data point, because the model will start to fit the noise, if it's a high capacity model.
Right.
And so we would like to use a held out prediction as if the model had never been trained on this data point.
Sounds good.
Yeah, so the way to do that is to do cross validation, and then you have every data point in your entire data set being held out from at least one copy of a model, and you can just use that copy to produce the prediction.
Sounds good. Thanks.
Okay, and so I'm going to just briefly talk about some principles of why the confident learning type of methods tend to be good. And so the three principles that are at play here is really the prune principle of just removing the errors, right, that are inferred, and then training. The count principle is using these ratios of counts rather than sort of any continuous model outputs, like direct use of predicted probabilities from the model. We're just converting everything into these counts in that C matrix. And finally, we are just using the rank of the model outputs to, as I mentioned, determine the top noisiest data points. And then we have the estimated fraction of data that's noisy in the data set, and we just remove those as the mislabeled ones. So here, nothing is really being done in the continuous world of predicted class probabilities, except for at the very beginning, comparing the predicted class probabilities against those class thresholds. And so what this really allows us to do is be much more robust against imperfect predicted probabilities. And all the methods that I talked about before, or a lot of them, are focused on modifying the loss function in some way. And they modify it in some way based on these predicted class probabilities to get a new loss function. But these predicted probabilities are, of course, estimated. So they have noise in them themselves. That noise propagates into your modified loss function. And of course, if you're doing like stochastic gradient descent or any kind of optimization, you end up with the noise affecting your resulting estimates a lot. And in our case, all we're doing is deleting, the things that we think are mislabeled. And so you don't end up with such a drastic problem of, actually tiny errors in these estimates affecting everything. It's more that maybe we deleted too many data points or too few data points overall, but still we're training on a valid data set. We're not modifying the data numerically in any way, or the loss numerically in any way. Also, this idea of counting. So for example, some of the more classical methods in this space tried to directly estimate the transition matrix of given versus observed label directly through these model predicted probabilities, some kind of averaging of them. Instead, in confident learning, it's doing a form of counting, right, of this matrix where it's thresholding these predicted probabilities and then counting things. And essentially, you can see that when we do this counting, it's almost like taking a median or like a robust statistic instead of just directly taking a mean over a bunch of continuous values, which is much, as everybody knows, from basic statistics, much more brittle to outliers and things like that, and sensitive overall. And again, the reason you have outliers and things like that is because we're using some arbitrary trained classifier. It is assumed that its estimates of these predicted probabilities will always be noisy. Maybe for some data, you get some out of distribution data point and it gives you a wild predicted class probability estimate. And that just does not affect the counts nearly as much as it would affect a straight up average of any sort over these predicted class probabilities that were used in early work. So, yep. That means these methods are just much more robust to the imperfect probabilities from our model. And the final thing I want to mention is like this thresholding, right, which I said was crucial. And so basically, let's assume that the model is producing errors like in all of its predicted probability estimates, right, where we add some kind of epsilon. And actually, what we find in real neural networks is they tend to be really overconfident for some classes, less overconfident for other classes. And so the epsilon can depend, on the class J. And, there's entire classes where the epsilon is non-zero. The model just has this propensity to like to predict certain classes and not others. But that actually will show up in our threshold, right? Because the threshold is just an average over a bunch of predictions, predicted probabilities. So if all the probabilities are overconfident, then the overconfidence is also reflected in the threshold itself. And then when we compute our counts, where we're comparing predicted probabilities, which are overconfident, against thresholds, which are also overconfident, these two terms cancel out. And so it allows this method to naturally account for the model's incorrect propensity to like to predict certain classes more than other classes. So I'm going to skip this, but basically we evaluate this on a bunch of toy problems where we just introduce noise with all kinds of models, all kinds of data to just really get the idea across that this is super flexible. And we find it always improves the accuracy, this process of identifying the label errors algorithmically, deleting them, and then measuring, retraining the exact same model on measuring its accuracy on correctly labeled test data. And then what we did more recently was we applied these algorithms to these famous ML benchmarks, and we looked at the test data specifically. And we measured, so we ran these algorithms to estimate how much of the test data was mislabeled. Then we took that estimated mislabeled data and passed it to Mechanical Turk workers who validated the labels. And essentially, we found that about 3.4% of these labels were incorrect on average over all the data sets, with some being much noisier than others in the farthest right corner. And the natural question is, so all I talked about before was the implications of label errors in your training data, right? Where obviously it's not a good idea to train your model on mislabeled data because then it influences the model's predictions on future data encountered during deployment. And here I'm going to talk briefly about the implications of test label errors in your test data. So here, for example, we have the same trained model on the left and right, same decision boundaries. And we have a mislabeled test set that we're evaluating the accuracy on the left, and correctly labeled the true underlying labels on the right. And so on the noisily labeled training test data, it looks like this model is 100% accurate, but actually it's not. And so that can influence decisions like, should I even deploy this model or not, right? You're typically just measuring how good the model is to make that decision. And so we need to clean up test data to be sure, that we're making decisions like that appropriately. So I think I already talked about this, but basically this is just walking through the Mechanical Turk interface we used to decide. We passed all these images where Confident Learning had flagged them as being mislabeled to Mechanical Turk workers and asked them, and we also took the prediction from the model for that image, like which class did it predict, and we asked them which class is better, or do neither of the classes apply, do both of them apply, things like that. And so here I'm going to focus just on the subset of these errors that we considered correctable, which is that Mechanical Turk workers agreed one of the other classes applied to the image and was more appropriate than the given label. And here we're going to ask basically how much noise in these benchmarks would lead to potential destabilization or us drawing incorrect conclusions from these benchmarks. And so here we take two machine learning models, ResNet 50 and a ResNet 18, and we're just looking at them in terms their test accuracy for ImageNet on the original labels in ImageNet. And what we did was we measured different test sets of ImageNet, just by sampling, where we increased the prevalence of errors versus not having errors in the test sets. So the percentage of data that was had a correctable label in the test set. And you can see here, if you measure the accuracy now just on the original labels originally given in the data set, ResNet 50 looks better than ResNet 18, uniformly across all these test sets. And that's sort of in line with all the literature. But what happens if we correct the test labels? So, everyone expects ResNet 50 to be better than ResNet 18. It's a much bigger model with more parameters. But actually, if we evaluate their accuracy on these corrected labels, we found that the ResNet 18 can actually be better in certain settings if the noise prevalence is high in the data, specifically around 9% here. And so what that means is basically that, because you're measuring these test accuracy on noisy given labels that are not necessarily true labels, you're also measuring the model's tendencies to not overfit in the traditional sense, but overfit in the distributional sense. They're able to fit this distribution of label noise better when they are higher capacity models than lower capacity models like ResNet 18. And so you see actually there's this insidious effect that maybe in certain cases when you have really mislabeled data, it might actually be better to use a simpler model because the simpler model simply doesn't have the same capacity to fit certain kinds of complicated mislabeling patterns. And then very briefly, I will talk about a natural extension of all this work to data labeled by multiple annotators. Obviously, if you know your labels are noisy, a natural strategy to deal with that is just to say, okay, instead of having one person label each data point, I'm going to have a few people label each data point. And so, here you might have 3 people labeling a data point, and you might ask, after this process, what was the best consensus label? How confident am I the consensus label is correct? And you might also be interested in discovering, which annotators are doing well versus not doing well. And I'll probably skip through notation given we're low on time. But obviously in such data, some annotators are providing less accurate labels than other annotators. And again, 3 quantities we might be interested in estimating are a consensus label for each example that aggregates all the individual annotations into our best guess of what the true label should be, a quality score for each consensus label that measures, how confident are we that the current consensus label that we just estimated in step 1 is actually correct. Intuitively, if we had more annotators labeling the image, we should be more confident, and they all agree, then we should be more confident that the consensus label truly is correct, as well as a quality score for each annotator, which estimates the overall correctness of their labels. And so a really simple baseline that most people would use for answering such questions, given a multi-annotator data set, would be a majority vote based method and using the agreement between annotators to determine, like how likely is it that the current consensus label is correct or not. So here, the consensus label would just be the label that most of the annotators chose for each example. The confidence score for how likely we think the consensus label is correct or not would just be how many of the annotators actually agreed with that consensus label. And then we might just rank the annotators based on, how often did this annotator over all the examples they labeled agree with the consensus label. This approach has a bunch of problems. One is it's not taking into account the quality of the annotators at all. So, bad annotators and good annotators are influencing this equally. Furthermore, it's really not reliable for examples that have only been labeled by one annotator or 2 annotators, right? Those examples, this majority vote type procedure is just not giving you too much information. The agreement is just very crude. And so essentially what we propose to do is train a classifier model just like we did in confident learning. It can be any classifier model. You get the predicted class probabilities from that classifier model. Then what you can do is form an ensemble prediction using the predicted probabilities from the classifier model, as well as treating each of the annotators themselves as if they were other models producing predictions. You basically treat them as if they're giving you predictions for each data point. And you form an ensemble predictor with weights assigned to the classifier model as well as each annotator. The weights are roughly estimated based on an estimated trustworthiness factor for each annotator relative to the trained model. How good is each annotator relative to the trained model? And for more details, you can refer to our paper below on how we estimate those weights. But broadly speaking, when you formulate the problem like this, you're really properly accounting for the number of annotations that each example had, because if an example had many annotations, then there's many WJ terms here, many annotators. And so the overall weight outweighs the classifier model significantly, and you trust, the agreement between the annotators then much more than any of the predictions given to you by the classifier model. Versus if you have a very accurate classifier model, then you trust the classifier model more. You're also here taking into account, the confidence of the classifier model itself, because you're using this probabilistic formulation from the classifier model. And so, yeah, this really gets you the best of all worlds and works well also for data where some data points are labeled by a lot of annotators, some data points are only labeled by one annotator. And you can really start to see good consensus score, get good consensus labels this way. So here we're just evaluating the accuracy of consensus labels from real image data, from real CFAR10 data labeled by 1 to 10 human annotators. And we compare it against, classical algorithms like Dawid-Skeen and GLAD, as well as classifier augmented versions of those classical crowdsourcing algorithms. And just we see that the resulting consensus labels you get from this approach are much more accurate. And yeah, for more details, you can refer to our paper down here. I think I'm pretty much at time, but if you want me to keep going, I'm happy to.
Yeah, we can probably go for another 5 minutes.
Okay.
Yeah.
So here we also evaluate how good this approach is at estimating the quality of these consensus labels. Again, when I say quality, I mean if we sort all the data by the quality score for the consensus label, and then we measure against how highly ranked are those consensus labels that were actually incorrect versus the true label versus the consensus labels that were correct versus the true label. We find that the quality scores we get out of this approach, and just to be clear, the quality score that we compute is just in the end, we take this ensemble estimate and we measure what's the probability this ensemble estimate assigns to the consensus label. So it's really, really dead simple. And we find basically that if we measure the alignment between the rankings according to the quality scores and the 0-1 ground truth, was the consensus label correct or not? Those two things align much better when the quality scores are coming from this approach I just outlined versus a ton of other methods. Similarly, if we compute the ranking between annotators, how good the annotators really are when measuring them against ground truth labels over all the examples that they did annotate versus the estimated quality scores for each annotator, we find that this approach just gives you much stronger alignment between the estimated rankings of annotators and the ground truth quality of the annotators' rankings. And so, yeah, this is a really useful way to curate a data set that you have already, labeled with multiple annotators, where some, especially when in settings where some data points were labeled by one annotator and some data points were labeled by many annotators. And finally, I'm going to talk about a brief extension of that to the setting where you're not only trying to curate an existing data set, which was already labeled by these annotators, but you're actually trying to collect new labels from new annotators potentially. And so in this setting, the key question that has not really been studied much in academic research, but is very relevant in the real world, is that the annotators are giving you imperfect labels, as I mentioned, in a lot of these settings, especially, any sort of Mechanical Turk, Scale AI, Label Box, using any of these services, the labels are highly, highly imperfect that you're getting back. And so in the setting, a natural question is, okay, I have this budget to label data. Should I label new data that I haven't gotten any labels for yet, or should I actually revisit some of my other data points that I did get some labels for, but maybe I'm not really confident in the current consensus label for those? And so in this setting, you have some data that's already labeled, some data that's not labeled yet at all. And the data that's already labeled, some of those examples may have one annotation, some may have more than one already. And the idea is to produce a score for both all the labeled data and all the unlabeled data, such that if we just take, the top 50 data points with the lowest scores, those are the ones that if we collect one additional label for each of those data points, regardless if they're originally labeled or not, that would be better for retraining a classifier model than any other set of 50 data points that we could have gathered. And so this is just a standard active learning problem in some sense, where you're establishing consensus labels just using the CROWDLAB method, say I previously outlined for all your labeled data. Then you train a classifier model with those consensus labels on the labeled data. Then you get predicted probabilities for all the data points, including the unlabeled data. You use some kind of active learning method to score all the examples based on those predicted probabilities, and then you just take the top, highest or lowest scoring examples and collect one additional label for each data point amongst those and add those additional labels to the training data and repeat this process. And so the way we assemble these, we do this scoring is just using this CROWDLAB algorithm. The only twist is we add an extra dummy annotator to this ensemble that I mentioned in CROWDLAB. And this dummy annotator assigns uniformly random label probabilities, just uniform distribution 1/k for every class and for every data point, whether it's labeled or unlabeled. And essentially we're saying, this annotator has no information about an unlabeled data point. Then we just compute the resulting CROWDLAB scores. And that is essentially the active learning score we use to decide whether or not to label that this data point should be part of the batch that will be the highest priority set of data to label next round. And the purple curve here, training, whether it's tree ensembles or neural networks or any other kinds of models, we tried on a bunch of different models and image and tabular data sets. We find that this approach just gives you much better models in the end when you're training the resulting model on the resulting consensus label from whatever data you have labeled so far than other active learning methods, like based on the entropy of the predicted probabilities or the uncertainty in the predicted probabilities or just random selection. And the final thing I'll emphasize is even if you have infinitely amounts of unlabeled data, you might think you always just want to keep labeling unlabeled data, right? Because I have infinite amounts of it. But actually, we found that if the labeling is noisy and not even super noisy, even at like 10%, it's actually can be better to sometimes relabel your existing labeled data than to always just keep labeling new data. And that's, yeah, an interesting phenomenon. We don't have, any theoretical explanation for this or anything. Obviously, when the labels are perfect, there's no reason to ever relabel data because your labels are perfect, of course. And yeah, that's all I have to say.
Okay, thank you, Jonas. It was very informative. Covered a lot of stuff. Let's give Jonas a round of applause. Don't see an applause reaction, but I can give you a coffee. Okay, more questions for Jonas from the audience.
I had a question. So just thank you for the talk, first of all. And first, I just wanted to sort of ask you about the data sets that you guys used, and a lot of the results that you showed were things like ImageNet and CFAR10 and stuff. Mm-hmm. So I guess the least sort of number of labels in the data set that you guys showed was 10, right? I'm guessing MNIST or CFAR10. Have you ever seen, like, in practice, like, I'm just thinking of the challenges that you might face with like binary classification, like tasks to detect noise labels. I think it would be much more challenging in certain domains to detect like binary class sort of labels. So I just wanted your thoughts on that.
Yeah, actually it's not. So that's a really common use case, and some of the big industry use cases of this package that were not done by us, but others is, so our CleanLab package implements this confident learning algorithm, and some really big use cases of it have been for audio data. So a common example of audio data is the use of a wake word for like an assistant, in Google Assistant or Amazon Alexa, and that's just a binary classification task there of whether or not the assistant correctly, or the annotators for that data correctly annotated the wake word being spoken or not. As well as another really common use case in binary classification is for fraud detection. A lot of banks, banking groups have been using it for fraud detection, which again is a binary classification there. The most common class of label error is that something was fraud, but it wasn't labeled as such, right? But if something was labeled fraud, it usually was fraud. There's not many, false positive labels, but there is a lot of false negative labels. And yeah, we see no problem in those settings, but in those settings, it makes it very clear, right, that the random, uniformly at random noise assumption would be totally incorrect, because certainly flipping rates are very not random.
Yeah, that's the reason I asked that. Thank you.
Mm-hmm.
So Jonas, I have a question. So you said this is now a product. So what sort of service does the product offer more than the library, and what sort of use cases are you seeing this being used for?
Yeah, so I can give some plugs. If you want to learn more about data-centric AI, we just recently taught this course. You can check it out here. And essentially, the key idea of everything we do is that you if you think about how a normal machine learning problem is addressed, you start by exploring the data, fixing some basic, very low level issues, transforming the data to be machine learning appropriate. Then you train your first machine learning model. And then what a lot of people will do is just jump straight into, hyperparameter tuning, training tricks, data augmentation, loss functions, modeling improvements upon the baseline model. But really the key thing we hope to emphasize is that you can use this model to detect a lot more problems in your data and improve the data set more, and then retrain another version of the baseline model before you jump into, the modeling improvements. And then actually, once you've done modeling improvements, you can even jump back into using the now improved model to find even better issues in the data set and further improve the data, this sort of idea of this feedback loop or virtuous cycle. And so how our open source works is it works really with almost any kind of data and any kind of machine learning model, mainly classification models, but also entity recognition, multi-label classification models, and others. We're working on extending it to basically all supervised learning tasks. And that makes the open source library really general, right? Because it works for any data, it works with any kind of model you already have. And then you can use that model to detect issues using the algorithms we have implemented for you in our library, which is here. And it will give you back basically what it thinks are some scores, like in active learning, or some estimates of consensus labels, like I mentioned for CROWDLAB, or some estimates of which data is mislabeled if you're using confident learning. But these are all estimates. It's really up to you what you do with those estimates to improve your data set. And so we also sell enterprise products, which are cloud SaaS software, in which we provide the model for you. So you don't have to, already have a reasonable baseline model. We use automated machine learning techniques to provide a model for you. And that's sort of a big trend of why we think data-centric AI now is the time for data-centric AI, is just the fact that we're even able to do that and train a pretty good baseline model on almost anybody's data set is just a testament to, how far we've come in deep learning and machine learning in general, and being able to produce good models using just automated code. So that's one thing we provide. And then we also provide an interface. So then we run a lot of the same algorithms on top of that model in our platform to surface issues to you, but we do it in a way that is with nice user interface so that you can actually fix those issues efficiently. So as I mentioned, like if we flag all the mislabeled data, it's never going to be perfectly flagged, right? This is a total statistical estimate. And so actually by presenting you what we think the mislabeled data is in a very nice interface that allows you to fix it as efficiently as possible, for example, fixing all similar looking examples with one click, things like that, you can actually improve your data set much faster that way. And so the whole product there is like a no-code product that does everything for you. But of course, it's less flexible. It only works for text data, image data, and tabular data right now, and we're hoping to extend it to audio data, whereas the open source model will always just be a lot more flexible because we're not providing any model for you or saying we know anything about your data. It's up to you to get a good baseline model for your data before you start using the open source.
Got it. Sounds good. Thank you. And is the CROWDLAB thing also integrated with this? Because
so all this stuff is just one line of code in the open source. This is the code to do that confident learning where you, this thing will automatically delete the label errors from your data set. This will automatically produce those CROWDLAB estimates for multi-annotator data. This will automatically give you those active learning scores. It's all of it is just one line of code in the open source. But again, you see in all of these cases, we are taking in predictions from a trained model, these pred-prob objects.
Sounds good. Okay. Thank you again. So I think we can wrap up here. Thank you again, Jonas, for visiting us and for sharing about CleanLab and all your research as well. All the best for the product growth. And thank you to the audience for joining.
Thank you so much. It was a lot of fun.
Take care. Bye.
Bye.